Today we're going to learn about using vectors in calculus. First, we have some basic notation. Most of this is geometry notation. Pay attention to the second one up here. That's much more important than the first one. The first one talks about how vectors are like translations, where we start with the point x, y, and then we move right 3 and up 4. But that's not as important as just writing this. So the 3 tells us what our movement is like in the x direction, and 4 tells us what our movement is like in the y direction. And the important part of this, it's not written like a point. It doesn't have parentheses, it doesn't have brackets, it has these little pointy brackets. So you have to have that to show that it's a vector. And if you see those, it's always a vector. Vector equations are very similar to parametric equations, so vector notation can almost be thought of as a different way to write parametric equations. So we have our brackets, our pointy brackets, and then whatever your x equation is for your parametric, that tells us how we're moving in the x direction, so that can go in the x part of the vector. And then same thing with y, can go in the y part of the vector. Because vectors are so similar to parametric equations, taking the derivative also feels very similar. So we have an example down here of vector u, and notice that the little symbol above it that looks like half of an arrow, that is how we show that u is a vector. Alright, so if we have the vector u where u is cosine of t for the x component and tangent of t for the y component, we want the derivative of the vector. We just take the derivative of each part. So basically this is dx dt and this is dy dt, just very similar to how we have parametric equations. But instead of finding dy dx, we just leave it as its separate components like this. Vectors can be used for a lot of applications, but primarily in BC Calc you'll see them used for particle motion. So just a reminder, position, velocity, and acceleration are derivatives if you go in this direction. So velocity is the derivative of position, and then acceleration is the derivative of velocity. If you go the other direction, if we want to go from acceleration to velocity, we take the integral, and then from velocity to position is another integral. Here's an example that kind of has everything that you'll have to do with particle motion. Not everything, but a lot of stuff. So we have an object moving along a curve in the xy plane, which is just a regular Cartesian plane, with a position vector given by x of t, y of t. And they never use the word vector, but you can tell it's a vector because it's got the little pointy brackets. And then they tell us dx dt is cosine of 3t and dy dt is 3 sine of 2t for time between 0 and 3. And then they tell us that at t equals 2, the object, the position vector is 4, 5. So we have to find the velocity vector at t equals 2 is the very first thing. And then we have to find the total distance traveled from 0 to 1 for time, and then find the position vector at t equals 3. So for part A, we have to find the velocity at t equals 2, and they already tell us dx dt and dy dt, so that basically that makes up our velocity vector. All we have to do is plug in 2 to the things that they gave us. So dx dt is cosine of 3 times 2, and dy dt is 3 sine of 2 times 2, which is cosine of 6 and 3 sine of 4. If you want, you can get those in decimals. It depends. If it's through response, you don't have to. The total distance traveled on 0 to 1 is a little bit different. So we need to think about this like a parametric equation, and when we're thinking about total distance traveled by our particle, we're looking for the length of the curve to see what did our object move, like how far did our object move. So we need from 0 to 1, because that's the interval they told us, and then we have to find the length of the curve given dx dt and dy dt. So going back to our previous notes, or thinking about the Pythagorean theorem, we have the square root of dx dt squared plus dy dt squared, and then we can evaluate that integral with a calculator, which gives us 2.299. For the position at t equals 3, there's a few different ways that we can do this, but I'm going to just go with a very basic, straightforward way to do it. So we have the velocity vector because they told us dx dt and dy dt. So we need the position vector, which means we need to take the integral of the velocity vector. So if we take the integral, we just do each part. So this is the integral of cosine of 3t, and this is the integral of 3 sine of 2t. And then they told us at t equals 2, our position vector is 4, 5. So we just plug in t equals 2 right here, and we get we get x equals 4 and y equals 5, and then we have to solve to see what is our constant of integration for both of those. Once we have our constant of integration, we can rewrite the position vector with that constant in there. So this is x of t and this is y of t. And then we plug t equals 3 into those to get this and this. And if you get the decimals, I just did this with a calculator. We get 4.230 and 2.580. So that's our position vector at t equals 3. Alright, here's one for you to try. A moving particle has the position xt, y of t. That's pretty standard. The position of the particle is 2, 6 at time equals 1. The velocity vector is given by this equation, 1 minus 1 over t squared for the x, dx dt, and 2 plus 1 over t squared for dy dt. So find the acceleration vector at t equals 3 and find the position at t equals 3. So take a couple minutes, pause the video here, and once you've worked out the problem, then unpause the video and look at the solutions for it. So the velocity they already gave us, we just have to take the derivative of each part. So derivative for the first part is 2t to the negative 3, and then the next for the y is negative 2t to the negative 3. And then we just plug in 3, so we get 2 over 3 cubed and negative 2 over 3 cubed, or 227s and negative 227s. For part B, I have a different method up here than we did for the example problem, just so you can see both methods, not that you have to do it this way. The other method works just fine too. But if we take the integral, so for the position of the x position, we can take the integral from the position we already have at t equals 1 to the position we want at t equals 3 of dx dt. And then we just have to add our initial position. So our initial x was 2. And when I say initial, I mean the position at t equals 1. And then if we evaluate that integral, we get 10 thirds. So same thing with y of 3. We take the integral of our velocity, and then we do it from our known position, which was at t equals 1, to our the position we want at t equals 3, and then we add the initial position, which was the position at t equals 1. And when we evaluate that integral, we get 32 over 3. So our position at t equals 3 is 10 thirds and 32 thirds for x and y. To find the magnitude of a vector, it's a little bit different. This kind of goes back to parametric equations when you're looking at finding the length of a curve. So we show magnitude by using absolute value signs. It's a vector v because it's got the little half arrow on top of it. This notation right here is not really used, but I just want to point out that the x component is x and the y component is y for notation. So to find the magnitude, so you would say the magnitude of vector v is equal to the x component squared plus the y component squared, and then we take the square root. And this comes from the Pythagorean theorem. So we're trying to find the length of the vector, and we have to do that using a triangle. So the length, our vector is the hypotenuse for our triangle, which gives us this formula for the magnitude. Alright, so for this example, we're trying to find the speed at t equals 2 of an object whose velocity is this and this. So the first one is our dx dt, and the second one's dy dt. And remember, speed is the absolute value of velocity, and then when we find absolute value of velocity, we do the Pythagorean theorem, essentially. So we plug in our x, we plug in our y, and then they tell us that this is at t equals 2, so we plug in 2 to get 13 squared and negative 3 squared, which is 9. And here's just arithmetic, plug it into your calculator, and we get the speed is equal to 13.342. And those are the end of the notes for vectors. So remember, as always, if you have questions, please ask me. If you're not watching this video in class, then write down your questions and ask me the next time you see me.